Okay, so thank you for the presentation. I'm going to present the work mechanical behavior of specimens made by a fused deposition modeling and the three-point bending, and it's the result from the collaboration between the Universidad from Madrid and the Universidad Politécnica de Valencia from Spain too. And these are the contents and the order I will follow in the presentation. As always, starting with an introduction about the 3D printing. Second, with materials and methods, with the printing material we use, the specimens that we manufacture, the experimental tests, unit substitution test for the characterization of the material, and then 3-point bending test. And we generated a numerical model based on a phase field fractal model. As we explained, I will make a brief summary. Then the results, okay, for the uniaxial tensile test and the 3-point bending test, and then the fracture predictions, okay, for that. And finally, the conclusion. We'll start with the introduction. Well, these are some advantages of the fused deposition modeling, as we were talking about in this session, or 3D printing, whatever we want, like the exponential work of interest, the possibilities of complex manufacturing, and a large variety of materials and properties. There are some disadvantages, like the influence of many variables in the problem and the printing defects, of course. And all these possibilities and the lack of knowledge in this field generate many questions to study. And we consider very important the fractal morphology of these kind of 3D printed components because of the anisotropic behavior of these components, the complex geometry to analyze because of the deposited filament with pattern we will see later, and the influence of strain rate on the results and in the fractal. Okay, so when we think about 3D printed composites, components, we think about inner infill with outer surfaces, so maybe we can consider some similarities with sandwich composites, like a honeycomb pattern and exterior shells, and the interest in bending behavior or in fracture. But there are numerous works, there are many works about this matter in sandwich composites, but few of them for 3D printing. Even though this is becoming a very cost-efficient alternative for all these components in some cases. And the same happens with some common tests like the 3-point bending, that there are a few works about it for 3D printing components, like the reference below, that studies this problem but from a global view. So, two topics that we consider very important are the analysis of fractal patterns and mechanical behavior at mesoscale view, and the study of defects and their influence on the results. Okay, so the aim of this study is the analysis of fracture path in PLA specimens under 3-point bending. We will focus just on no-shell specimens, okay, just with an infill and a grid pattern infill, and this will allow us to study these widely common lattice architecture, okay, in this kind of specimens. For that, we are going to implement the digital metric correction technique to study the strain field in all these tests, and numerical analysis, as I mentioned before, with a phase field prediction. Okay, the materials and methods. We will start with the manufacturing of the specimens. We used a PLA filament using a layer height of 0.4 millimeters and a nozzle diameter of 1 millimeter. And on the left, you have the tensile sample, the drawing design. It was manufacturing on a full density, okay, 100% density, and a thickness of 4 millimeters, as you see there. And on the right, the prismatic samples. The dimensions, length of 100 millimeter and a cross section of 10 by 20 square millimeters. As I said before, we used the grid pattern for the infill, and we manufactured 3 different infill densities, 30, 50, and 75% to study these parameters too. Okay. Regarding the experimental tests, for both tests we use the testing machine you see there with a load cell of 10 kN and the implementation of digital mesh correlation. for the uniaxial tensile test, you have there the setup. We used an extensometer, okay, to obtain the strain more accurately, okay, and we make it at two different test velocity, 1 and 15 meters per minute, to study the strain rate, okay. Then on the right, the 3-point bending test setup there with a test velocity of 1 millimeter to ensure the to ensure the static conditions, and some other parameters like the distance between supports and the diameter of these supports. Okay, so as I told you, we used very well. I will tell you later. Phase field fracture model for the prediction of the failure. Okay, so as a brief summary, we'll use a continuous variable phi going from 0 to 1, and to describe the nucleation and the growth of the graph. Okay, so 0 means that there is no damage in the material, and 1 that the material is scrapped. We have here on the figure on the right an example of a general body, 2D in this case, but well, could be in 3D, of a diffuse crack, okay, because this variable defines the crack in a diffuse way, going from 0 to 1, and we can see here how the material is losing its strength till the crack phase on the black line, okay, here. What happened with this line on red? This is the phase field profile, okay? And it defines the evolution or the distribution of this parameter along this perpendicular, okay? And we have some examples here, okay? Depending on the length scale parameter that I will tell you now. This distribution of the phase field depends on the combination of some parameters and functions, like the length scale parameter, as I told you, okay? We have here some examples, sorry, and the geometric crack function for the distribution of the phase field, and then to complete the model, we have to apply energy degradation function to compensate the increases of the fracture energy, and then we can apply, depending on our test, the energy split to separate traction and compressive forces and irreversibility methods. But well, this is a brief summary, so it's not the main part of the work. So we can continue with the application, or the application of this phase field. This model, it's an interpretation of the Griffith's criterion as a variational principle, and how can we include the evolution of this phase field in the fracture energy like that? Okay, we can make this approximation. Then we have a lot of formulation, but we don't have time to talk about it. And in our model, I use the implementation Larkus by Mediterranean, okay, and these are all the parameters that we use from our own tests and from the literature, okay, and some methods, as I told you before, for preventing the cracking and compression, sort of traction forces, and so on. You have there the two-dimensional model of the 50% infill density, and you can notice the small size that is required in this kind of method. Okay, so we can start with the results. Firstly, from the uniaxial tensile test for the characterization of the material. On the left, we have two curves, two force displacement curves for 1 and 50 mm/minute. And while you can see that while the 1 mm/minute reaches a stabilization zone with large displacement, when we increase this strain rate, the fracture is immediate, okay, in very low displacement. And on the right, to calculate the jump modulus and everything, we have the stress strain curve from the extensometer, and it helps us to validate the BIC response. Okay, you can see the elastic recovery of the material here in our region of interest, and in the middle the table with the some main the main PLA mechanical properties like the apparent joint modulus, the Poisson coefficient, and the tensile strength that we use in the model, in the numerical model. Yeah, now with the three-point bending test for the 30, 50, and 75% specimen. Here are the force displacement curves again, and below the before and after specimens, before and after bending, sorry. On the case of the 30% specimen, we can see again large displacements, okay? Then for the 50 and 75%, an abrupt fracture, okay? In lower displacements. And as expected, the maximum force is increasing while we increase the percentage of the infield. Okay, so just for the 50% specimen, we have here the crack path of the specimen, okay, with the two supports and the moving punching, and this crack path goes from 1 to 3, from 1 to 4, okay. These are the joints of the infield, and here we have the result of the DAC, the digital mass correlation, the strain in each joint, okay. You can notice that in the first two joints, the strains are much bigger than on the other ones. The other ones are, the fracture is immediate. And we can see this too from a microscope view. Okay, these are again the four joints of the crack path. In the first and two, we can see some plasticity next. Well, this is after the fracture, okay, but this is forming before the fracture. And then on the third joint that is in the middle of the neutral fiber of the specimen, we can see like an intact filament here, and then an abrupt fracture because this is a rough surface. Okay, this seems like a rough surface. So, talking about the fracture predictions, this is the result of the simulation, the preliminary simulation. Okay, this is as we expected. The crack path simulated. Okay, from this crack path is along the minimum cross section next to the middle of the specimen. And remember, this is the value of 1 for the phase field parameter. Okay, that means that the material has lost its strength, and its craft. Okay, here if we compare. Yep. One. Okay. If we compare the numerical and experiment results, we can see that the result is not the same. Okay. What that means? Well, it could be explained by the fact that the numerical model has no printing defects. Okay, it's a perfect repetitive geometry for the grid pattern, and then the opposite happened with the 3D printed specimens with some critical imperfection. Okay, that could lead the crack path. Okay, now what we conclude with this that this microplasticity nets that I mentioned before are generated because of the grid pattern. Okay, you have there on the right the nozzle trajectory to complete just one line. Okay, and we can see that the nozzle passes through each joint 2 times. So this generates accumulation of material. On the left, you have the overlap filaments before the bending, that they reduce the diameter of each filament in each wire, and then after the bending, the start growing of the neck forward. Then, to study this failure on detail, we manufactured this cross-shaped specimen. Okay, you should know that this was printed before this vertical line, and then the horizontal one from right to left. Okay, so you can see how after the first deposited filament, the nozzle, when the material is deposited before this first line, the material is accumulated in this zone. Okay, so the cross section here is high, is very wide. The opposite happened in the other side. The material accumulated in this way, but on the other side, the section is very low. Okay, so we conclude that this is where and we validated that in this zone the failure initiates. Okay, and we have here two images of the CT scan to see that. Okay, even with bullets. And as a conclusion, very fast, the fracture is significantly influenced by FDM process parameters, like the nozzle trajectory, of course, as we studied. The infill density directly affects failure mechanisms and the three-point bending. The crack path analysis and DAC technique provide important information of manufacturing defects affecting failure. Okay, and numerical models should include printing defects to predict crack path, as we see here. That was everything. Thank you so much.
We have time for a quick question from the audience.
Yeah.
Let's get from in phase field has an important role. How did you calculate it or calculate it?
What? So, right? Yeah. Well, as I said, this was a preliminary simulation just to see the graph out as I expected, but yeah, this is very important. Maybe you know, but yeah, the length scale parameter describes this width of the diffuse crack, okay? And then we use the 0.79 like the literature. I think, yeah, I don't put it the reference, but yeah.
How did you consider this number? You calculate it because the original mathematical solution for only yes, I don't know, how did you calculate it? Or how did you measure the L0?
Yeah.
That,
yeah, thanks. That parameter is very important. Well, this was from the literature, okay? Yes, but this parameter is very important, but because some authors consider that this parameter is a material property. So you can consider it as a material property, and in future works, I will make some not to specimen and we will test it in that way. And I think I will consider it like a material property, and I think we can validate it. Yeah. Thanks.
There was another question, very fast.
How was during the experiment? How is it sure that the loading was applied just on the crossing node of this specimen? That it was not shifted between these two nodes?
Yeah. It was just sorry. Yeah, well, something like this. Okay, here. You mean? Yeah. After this work, we made some other works that this corner here goes till the end of the specimen. Okay. We had to change the 50% density. I think it was 58% to reach this corner. But yeah, we did it manually. Like yeah, we put it in the middle. Yeah, and we just used the good results in the experimental test because yeah, we did like 5 of them.
In the middle, there is not symmetry in crack initiation.
Yeah. But we think it's because of well, if you see this, yes, we think it's because of the lower section of the arms that we studied later. Yeah, we think it's about it.
It's a pity that it is not in the center of the specimen.
Yeah, it started like that. Yeah. This is suspected, but then should be this one, like in the simulation. But yeah, this is a lower section joint 2, and then through the middle, and again. It's everything because of the conclusion. Well, we consider that because of this difference between one side and the other one.
Okay, thank you very much again.